The silence coming from Elon Musk isn't accidental. While he avoids giving away crucial details about Tesla's next big move, something monumental is unfolding inside Tesla's global factories. Across Gigafactory, Texas, Nevada, Berlin, and Shanghai, workers are restructuring production lines, updating machinery, and preparing for a vehicle that could append everything we believe about low-cost electric cars, internally labeled as the Model 2. This compact is expected to come in at just $11,799 is shaping up to be far more disruptive than Tesla is publicly acknowledging. But Tesla's secrecy invites bigger questions. Why hasn't the company openly confirmed its real production timeline? What enables Tesla to build a complete electric car at a price that would terrify long-established automakers? And why is Tesla deliberately avoiding discussion of certain engineering breakthroughs that make this unheard-of price even possible? Anyone who closely tracks Tesla knows that the company rarely reveals its full strategy up front. But the evidence hidden in patents, trade filings, environmental permits, supplier shipments, and foreign manufacturing documents paints a much clearer picture of what's really happening behind the scenes. Tesla's entire manufacturing model is undergoing a transformation so significant that it could cut production time in half, reduce component complexity by hundreds of parts, and enable simultaneous multi-continent production from day one. The public has only been shown a fraction of this reality. The rest is buried in technical documents that reveal a radically optimized assembly process designed specifically for this vehicle. The internal shift begins with a system Tesla calls unboxed assembly architecture. Unlike traditional automotive manufacturing where a car moves from one station to the next in strict sequence, Tesla's new approach splits the vehicle into independently assembled sections that only come together at the end. Years of data, engineering papers, and patent filings from September 2024 confirm that this architectural change eliminates nearly half of the steps required in a conventional production line. Ordinarily, a car progresses through 300 to 400 distinct stations, taking around 20 to 25 hours to build. But through parallelized assembly, Tesla compresses the Model 2's production down to around 160 steps, reaching a build time closer to 10 hours. That kind of efficiency is unheard of in the automotive world and drastically reduces labor requirements, factory floor space, and operational costs. Tesla isn't openly discussing this because the competitive implications are enormous. If legacy automakers realized Tesla's cost base had dropped this dramatically, they would see how impossible it will be to compete with the Model 2's price point. The $11,799 figure isn't a marketing stunt. It's the logical end result of an ultra-efficient vehicle architecture. But the biggest clues don't come from Tesla's announcements. They come from trade data. Supply chain documentation submitted to customs officials shows that the Model 2 relies on a structural battery pack that doubles as the vehicle's floor, eliminating the need for many underbody parts entirely. This concept evolved from the structural pack found in the Model Y, but the Model 2 uses an even more streamlined design. Instead of battery modules, it uses cell-to-pack construction, reducing the number of separate components by more than 370 parts compared to the Model 3. Engineers who have reviewed the internal filings estimate that this design alone saves between $1,200 and $10,000 per vehicle. Yet Tesla has never publicly walked through this architecture, likely to avoid giving rivals insights into how far ahead the company is on manufacturing efficiency. Then there's the geographic production strategy. Elon Musk publicly stated that the Model 2 would primarily be built in Texas, with future expansion happening later. But equipment imports and tooling shipments tell a completely different story. Beginning in late 2024 and continuing through early 2025, large volumes of casting machines, welding systems, robotics, hardware, and battery line equipment were delivered not just to Texas, but also to Shanghai and Berlin at the same time. This means Tesla isn't planning a phased rollout, it's preparing concurrent mass production in North America, Europe, and Asia immediately at launch. That never happens in the auto industry. Manufacturers almost always ramp production in one location first to minimize risk. Tesla, however, is creating capacity on multiple continents simultaneously. Why? Because the company learned from previous launches that long wait times can slow adoption, raise prices in certain markets, and give competitors time to catch up. If Tesla can flood global markets at once, it prevents regional shortages that could delay mass adoption. For consumers in large states like Texas, California, Florida, and New York, this means faster delivery timelines than anyone expects. Cars for southern and central U.S. buyers will come from Texas, while East Coast buyers may receive cars produced in Germany, an unexpected yet highly efficient arrangement. This eliminates costly cross-country shipping and minimizes regional supply mismatches. Another buried clue emerges from environmental permit filings for Tesla's upcoming Mexico Gigafactory and the Texas facility. These documents mention a new in-mold color coding process. This process applies paint directly into the molded exterior panels, reducing painting steps and emissions. But it comes with a major limitation. Tesla will only offer 3 or 4 initial colors, likely white, black, silver, and possibly blue. It's unusual for Tesla to limit paint options so severely, and the company hasn't stated this publicly because it knows buyers expect broad customization. But the trade-off is worth it. This method dramatically cuts costs and speeds up production. Once all these manufacturing savings are understood, the question becomes, how does Tesla hit the incredibly low price of $11,799 without compromising performance? The answer lies in the hidden innovations behind its components. Starting with the battery. While Tesla claims the Model 2 uses standard LFP lithium iron phosphate batteries, internal regulatory filings expose something more advanced. The chemistry is what Tesla refers to as enhanced LFP, where manganese is added in a unique ratio. This boosts energy density by around 15% over typical LFP cells while retaining low cost and long battery life. Contracts with CATL, the suppliers, show that 35 GWh of this enhanced chemistry is allocated annually for a vehicle with specs nearly identical to the Model 2. That's enough capacity to build more than 500,000 vehicles each year. But the documents also reveal something even more intriguing. Tesla's energy division is testing a hybrid aluminum-lithium battery design using aluminum clusters in the anode. This breakthrough increases energy density to roughly 310 watt-hours per kilogram, about 28% higher than the batteries planned for the Model 2's initial version. The real significance is the charging speed. These prototype aluminum-based cells can charge from 10% to 80% in about 12 minutes using 350 kilowatts fast chargers. This is possible because aluminum's electron mobility and low resistance outperform traditional graphite anodes. However, the technology isn't ready for mass production due to durability issues. The cells degrade after roughly 1,000 cycles, equivalent to around 300,000 miles. Tesla's goal is to refine the electrolyte and stabilize expansion and contraction before rolling it out in late 2026 or 2027, when the aluminum battery eventually enters production. It could reduce material costs by more than 20% and significantly reduce Tesla's reliance on graphite. Imports an enormous win for U.S. manufacturing. Security, another major cost reduction, comes from the Model 2's electric motor. Instead of using permanent magnet motors, Tesla is adopting an externally excited synchronous reluctance motor. This eliminates rare earth elements entirely, avoiding price volatility linked to global rare earth supply. Rare earth magnets contribute around $400 to $600 to the cost of a single electric motor. Removing them not only cuts costs, but also makes the Model 2's supply chain far more stable. While this type of motor loses a small amount of efficiency, it still retains 90 to 95% of the efficiency found in magnet-based motors, an excellent balance for a budget. Tesla's interior strategy further reduces costs. Import records reveal the company is sourcing an engineered polymer textile, a durable, breathable composite fabric that costs around 40% less than synthetic leather. It meets durability standards, but offers a different tactile feel compared to the interiors of higher-priced. This cost difference won't be disclosed in marketing material, but it significantly contributes to the affordability of the Model 2. Tesla has also consolidated its electronics architecture. Instead of multiple computing units spread across the vehicle, the Model 2 uses a single integrated board that manages everything from infotainment to vehicle controls to driver assistance. This reduces wiring by 60% and lowers electronics costs by several $100s. Tesla's silence around the real production readiness of the $11,799 Model 2 has created an enormous gap between what the public believes and what is actually happening behind factory walls around the world. While Elon Musk continues to avoid confirming timelines or revealing engineering specifics, multiple Gigafactory operations are already deep into structural changes that leave no room for doubt. Tesla is preparing this vehicle far earlier, more aggressively and more efficiently than the company is letting on. Whether in Texas, Nevada, Berlin, or Shanghai, the shift is unmistakable. Production lines are being rebuilt, equipment is being installed months ahead of public schedules, and supplier contracts point to scaled manufacturing beginning sooner than anyone expected. What makes this even more remarkable is the price point. An EV priced at $11,799 seems impossible on the surface. Legacy manufacturers struggle to produce EVs under $35,000, even with simpler designs. Yet Tesla appears to be solving a puzzle that no other automaker has managed, combining ultra-low-cost engineering, next-gen battery chemistry, and a globally synchronized production model to drive down prices explosively. Under the surface, the reasons are much deeper than simply cheaper parts. Tesla is quietly reinventing how cars are designed, assembled, powered, and delivered. The real story begins with the unboxed assembly architecture. Tesla did acknowledge this system conceptually in late 2023, but the company never revealed how extensively it would be used or what it meant for cost reductions. Patent documents filed in 2024 paint a much clearer picture. Instead of building a vehicle frame as a single moving unit down a long assembly line, the Model 2 is built in several isolated zones where major sections are constructed simultaneously. Body structure, interior modules, electronics units, and the structural battery pack all emerge from different manufacturing branches and only come together near the very end. This alone allows Tesla to eliminate close to half of the traditional assembly stages required in a typical automotive plant. Traditional automakers use a heavily sequential process with around 300 to 400 individual build steps. The Model 2 compresses this into around 160, thanks to the parallel structure. It's the difference between building a car like a long conveyor belt versus assembling it like modular blocks. This change cuts production hours per vehicle from the industry. Standard of 20 to 25 hours down to about 10. Fewer steps mean fewer robots. Fewer people, fewer quality control bottlenecks, and far higher throughput per square foot. No automaker has ever been this close to building cars like smartphones' modular components coming together near the end, with minimal manual intervention. Another major hint comes from supply chain records. Data filed with customs authorities shows that the component sourcing for the Model 2 differs sharply from previous Tesla vehicles. One major change is the use of a new structural battery pack that functions as the vehicle's floor. It's not simply an evolution of the Model Y's structural pack, but a more radical design that removes modules entirely. Instead of cells arranged in modules that then fit into a pack, the cells are integrated directly into a reinforced load-bearing structure. This shift reduces the number of parts by several hundred. Engineers familiar with the filings note that the Model 2's pack removes nearly 370 individual components when compared to the Model 3's architecture. That translates into savings of around $1,200 to $1,800 per vehicle and battery structure costs alone. Tesla has never publicly acknowledged the exact version of cell 2-pack integration they are using. But supplier orders leave no room for doubt. This is not the same structural pack used in existing models. This is an entirely new category. Then there is the matter of where the Model 2 will be built. Public announcements paint a simple picture. Initial production will begin primarily in Giga, Texas. But equipment procurement records tell a different story. Specialized casting, welding, coating, and assembly machines have been shipped simultaneously to Shanghai and Berlin between October 2024 and January 2025. These aren't small test machines. They're large-scale production units. This level of deployment suggests that Tesla isn't thinking in terms of localized production, but simultaneous global manufacturing from the very start. For buyers, that means the rollout won't follow the typical pattern of one region getting vehicles months or years before the rest. Instead, Teslas could reach the US, Europe, and Asia on nearly the same timeline. This strategy balances global demand, prevents regional shortages, and stops competitors from capitalizing on early market gaps. It also means that your Model 2 in New York might not be built in Texas at all. It could be sourced from Berlin because it's closer and cheaper to ship. Another subtle but important piece of evidence comes from environmental permit filings in Texas and Mexico, where Tesla has outlined a new in-mold coating paint method. Traditional paint shops are extraordinarily expensive and slow, often costing hundreds of millions of dollars to install. The new paint process Tesla is deploying uses single-layer, ultra-thin coatings that bond directly to polymer-enhanced body panels. While this method is revolutionary, it comes with one catch: fewer initial color options. It appears likely that the Model 2 will launch with only 3 or 4 colors, possibly white, black, silver, and one additional option depending on region. Tesla hasn't mentioned this, but the regulatory filings make it unavoidable. The trade-off is efficiency and lower costs at the expense of early customization. Understanding how Tesla can price the Model 2 at $11,799 requires examining the unseen decisions behind the battery design, motor architecture, interior materials, electronics, and thermal systems. The battery chemistry itself is not a standard LFP. While Tesla officially uses LFP in many lower-range vehicles, regulatory and supplier documents reference an enhanced LFP formula that includes manganese in a unique ratio. This LFP-Mn variation boosts energy density by about 15%, while costing significantly less than nickel-based chemistries. The company providing much of the production capacity for this chemistry has allocated around 35 gigawatt-hours annually specifically for a Tesla vehicle that lines up perfectly with the Model 2's expected pack size. At 66 kilowatt-hours per pack, that capacity supports around 500,000 vehicles a year. However, Tesla's public communications have hinted at smaller packs, 53 to 60 kilowatt-hours. This mismatch implies that Tesla has either designed a pack with reserve capacity or is intentionally underreporting range estimates for competitive or regulatory reasons. Beyond that, Tesla is quietly testing aluminum-ion hybrid batteries at pilot scale. These experimental cells replace part of the graphite in the anode with aluminum clusters. Early prototypes have demonstrated astonishing energy density improvements, around 310 watt-hours per kilogram, which is nearly 30% higher than current LFP. Even more impressive is the charging performance, 10% to 80%. In roughly 12 minutes under high-power fast charging, this dramatic improvement is due to aluminum's exceptional electron mobility and low resistance during ion movement. But despite the breakthroughs, the tech is not yet stable enough for production due to electrolyte degradation during repeated cycles. Tesla appears to be targeting 2026 for mass deployment if the materials challenges can be resolved. If they succeed, the cost of battery materials could drop by more than 20%. This would be a massive competitive edge, especially for the North American market where graphite dependency remains a strategic weakness. Tesla's single quotes decision to avoid permanent magnet motors in the Model 2 is another major factor. Rare earth metals are volatile in price and heavily concentrated in specific, geopolitically sensitive regions. Component sourcing records confirm that the Model 2 uses an externally excited synchronous reluctance motor instead of the permanent magnet motors used in the Model 3, and why this motor design eliminates rare earth metals entirely. It's cheaper, saving about $400 to $600 per vehicle while still achieving roughly 90 to 95% of the efficiency of a permanent magnet motor. This is a small trade-off for efficiency, but a massive gain for cost reduction and long-term supply chain independence. Tesla did not advertise this change because discussing lower efficiency could compromise marketing narratives around range. Yet the numbers clearly favor this decision for a low-cost vehicle. The interior is another hidden cost optimization zone. Customs declarations show large shipments of a material called engineered polymer textile. This is not faux leather or traditional automotive cloth. It's a composite textile that costs about 40% less than Tesla's usual vegan leather. It's durable and lightweight, but the tactile feel will be different. Slightly less premium, more minimalist. Tesla is not disclosing this because interior quality is one of the first aspects customers judge emotionally. If expectations are set too high, disappointment could follow. By staying quiet, Tesla ensures that reactions only occur after customers sit inside the car rather than forming conclusions ahead of time. The computing system inside the Model 2 is also dramatically simplified. Instead of distributed computing with multiple controllers handling different systems infotainment, vehicle controls, driver assistance, the Model 2 uses a single board architecture. One computer manages everything. This reduces the wiring harness by about 60% and cuts electronics costs by up to $450 per car. The downside is that the computational headroom for future software upgrades is smaller. Cars W.